Okay, today we're looking at Chapter 10, Topic 8, multiplying probability of independent and dependent events. Independent event is an event in which the outcome of the first event does not affect the outcome of the second event. Okay, the roll of a die does not affect the flip of a coin. So to find the probability of independent events, we multiply the individual probabilities. So for instance, in a board game, 2 dice are rolled. What is the probability that the first shows a 6 and the second shows a 6? So we would say probability of A and B is probability of A times probability of B. So probability of A, first die showing a 6 is 1 over 6. Probability of B, second die showing a 6 is 1 over 6. So probability of A and B is 1 over 36. Now let's say that we wanted to prove that they were indeed independent. Okay, so to prove that they are independent, we would first have to look at what is the actual probability of rolling the first die a 6 and the second die a 6. So first we list out the sample space of rolling 2 die. Okay, these are all the different possibilities where the first roll, comma, second roll. Okay, so 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. 1, 2, 2, 2. So these are all the different possibilities. 36 different possibilities. 6 for the first roll, 6 for the second roll, so 6 times 6, 36. 6 options for the first roll and 6 options for the second roll, so 6 times 36. 6 times 6 is 36. There's only one place here where the first roll is a 6 and the second roll is a 6. So that would mean that there's a 1 over 36 chance that you roll a 6 followed by a 6. There's only one way out of 36 to roll a 6 and then another 6. Now we can prove that these two events are independent by showing that their probabilities together are the probability of the first event multiplied by the probability of the second event. And we already did this. A and B is equal to probability of A times probability of B. Well, we already did this. 1 over 6 times 1 over 6, which is 1 over 36. Now, since the probability of A times the probability of B is equal to the probability of A and B, we already showed that this is the correct calculation, then we can say that yes, they are independent. Now, if we had calculated probability of A times the probability of B and it wasn't 1 over 36, then they would not be independent because we already showed that the true probability is 1 over 36. Okay, so if this calculation is also 1 over 36, then they are independent. If this calculation is something else, then they're not independent. A card is shown from a standard deck. A card is drawn from a standard deck of cards. A spinner with 4 equal sections of different colors is spun. What is the probability of drawing a jack and the spinner landing on red? So we want the probability of jack and red. So that would be the probability of a jack times the probability of red. Okay, well the probability of a jack is 4 over 52. Probability of red, it's 4 equal sections of different colors, so 1 over 4. So that would be 1 over 52, probability of jack and red. Now that only applies if these are independent events. We need to prove that they are independent events. So we need to show that the actual probability of getting a jack and a red is 1 over 52. So let's look at how we would prove the actual probability here. Okay, so we know that there are 52 times 4 different possible outcomes, okay? So for the first event, there's 52 possibilities, and for the second event, there's 4 possibilities. So together, there's 208 different combinations of the events happening. Of those 208, 4 could be a jack and a red spin. Okay, you could have the jack of clubs and red. You could have the jack of spades and red. You could have the jack of hearts and red, or you could have the jack of diamonds and red. So there's 4 different possibilities out of those 208 that could be jack and spin red. So we know that the real possibility or probability of jack and red happening is 4 over 28, or 4 over 208. That's jack and spin red. All we need to do is show that that is equal to the probability of jack, times the probability of red. And we already showed that. Okay, 4 over 52 times 1 over 4, which is 4 over 208. So that means that they're independent because multiplying their probabilities together is equal to their intersection of jack and red. So they are independent, okay? Now, if we had multiplied the probability of jack and the probability of spinning red together, and they had been something different than the actual probability of the intersection of jack and red, then we could not say that they're independent. We also have dependent events in which the outcome of the first event affects the second event. Okay, an example of this would be drawing 2 or more cards from a standard deck without replacement. Okay, so the first event, drawing that first card and then not putting it back, is now going to affect the probability of drawing the second card because there's going to be one less card. So when you have dependent events, you calculate the probability of A and B in a different way. Okay, we say the probability of A and B is equal to the probability of A times the probability of B given A that has occurred. Okay, so that would be the probability of B given A has already happened. So let's see how this would apply. So a bag of marbles has 4 red, 3 blue, 2 yellow, and 3 green. 2 marbles are randomly drawn from the bag, one at a time, and not replaced. Find the probability that the first is red and the second is blue. So that's the probability of red and blue given that the probability of the first one, is equal to the probability of the first marble being red plus the probability of the second being blue. Sorry, I should write that as we have it here. I'll just have it as we got here. Probability of the first one being red and the second one blue is equal to the probability of the first one being red times the probability of the second blue given that the first one is red. Okay, so let's calculate this. The probability that the first one is red, well, there's 4 red out of 4, 7, 8, 9, out of 12, it looks like. Yeah, 12 marbles in total, so 4 over 12. Now we want the probability that the second is blue given that the first one is red. Okay, well, if the first one is red, then now we have 3 red, 3 blue, 2 yellow, and 3 green. Okay, because the first one's red. Now we have 1 less red. So now the probability is 3 out of 11 for drawing a blue marble given that the first one we drew was red. So that gives us a probability 1 over 11. Okay, so the probability of drawing the first one red and the second one blue is 1 over 11. A bag of marbles has 4 red, 3 blue, 2 yellow, and 3 green. 3 marbles are randomly drawn from the bag one at a time and not replaced. Find the probability that the first is green, second is green, and the third is red. Okay, so we got to extend this concept out to 3 events. So we want the probability of first green and second green and third red. And that's going to be the probability that the first is green times the probability that the second is green given the first one is green times the probability that the third is green given that the first one is green and the second one, sorry, not the third one is green, the third one's supposed to be red. The third one is red given that the first one is green and the second one is green. Okay, so the probability of the first one being green is 3 over 7, 8, 9, 3 over 12 times the probability of the second one being green given that the first one is green. So now that would be 2 greens left out of 11 marbles, so 2 over 11. And then the third one being red given that the first one is green and the second one is green. So we only have 1 green left, but we still have 4 reds. However, now we only have 10 die. So it looks like we'd have 1 over 55 chance of that happening. 3 over 12 times 2 over 11 times 4 over 10, 24 over 13, 20, which is 1 over 55. That's the probability that the first one is green and the second is green and the third is red. And then a little bit more on proving independence. Suppose 20% of our high school students are Gator fans, 40% are Seminole fans, and 18% are fans of both. Are these events independent? So if they're independent, then the probability of Gators and Seminoles would be equal to the probability of Gators times the probability of Seminoles. Okay, well, we already know that the probability of Gators and Seminoles, both of them, is 0.18. Probability of Gators is 0.2, and the probability of Seminoles is 0.4. Well, that's 0.08, when the true probability is 0.18. These are not equal to each other. Okay, so this formula only works for independent events, and it didn't work here. So these are dependent. Are these events independent? No, they are dependent. They're not independent. Let's just say that. No, not independent.